10 things that will make your brain feel genuinely broken. Let's go. Number 10. Event horizon. You cross an invisible line in space and you never come back. From a safe distance, a falling ship will appear to slow and then fade as it hugs the edge. From the ship, you feel only motion forward, as if every direction has been bent to point inward. The edge marks where escaping would require outrunning light itself, and nothing in the known universe can do that. Near the boundary, something stranger happens in the equations. Space and time swap roles. Moving outward stops being a direction you can choose, the way moving backward in time is not a direction you can choose right now. Rockets, thrust, acceleration, none of it matters once you cross. Signals sent from inside get stretched into long red whispers for anyone listening outside. They thin, they redden, they vanish. Physicists have argued for decades about what the edge actually is. Roger Penrose showed in 1965 that once a surface like this forms, the collapse to a singularity is inevitable. The math does not offer an exit. Some researchers say the crossing is smooth and quiet. Others, following work by Almhiri, Merrill, Polchinski, and Sully in 2012, warn of a firewall, a searing wall of quantum energy that would incinerate anything attempting to pass. More recent proposals suggest quantum entanglement islands might preserve information in subtle ways we are only beginning to sketch. Cross the line, and whatever you were, your mass, your history, your structure, is cut off from the rest of the cosmos. From your ship, the fall feels ordinary. To someone watching from a safe distance, your image stretches, dims, and freezes on the boundary like a photograph slowly bleaching in sunlight. You are gone, but your ghost lingers. We even have pictures now. The Event Horizon Telescope collaboration published the first image of that dark silhouette in 2019, a bright ring of superheated gas circling the shadow of M87 star. Those images do not show the interior. They show what happens when light tries to leave and fails. The edge is where general relativity and quantum mechanics collide, and neither theory walks away clean. Number 9. Spaghettification. You fall feet first toward a compact object and your feet feel a pull dramatically stronger than your head. The difference across less than 2 meters of body is the entire story. Gravity weakens with distance. Near something dense enough, as that weakening becomes savage across the span of a human frame. One end of you accelerates while the other lags behind. The result is elongation, a slow then rapid stretching. Your body pulls apart like warm glass being drawn into fiber. For a stellar mass remnant a few kilometers across, the tidal gradient spikes almost instantly. Destruction arrives before your nervous system can register the first signal of pain. For a supermassive object like the one at the heart of Messier 87, the gradient rises far more gradually, and the process could unfold over minutes as you are slowly drawn into a luminous thread. Your body does not merely stretch. Friction between layers of tissue heats the material. Tidal shear tears molecules apart. Bone, muscle, and water become a stream of ionized plasma spiraling inward along magnetic field lines. Astronomers have watched the same physics shred entire stars. They call these events tidal disruption events, or TDEs. In 2020, the Zwicky Transient Facility caught a star roughly the mass of our Sun being torn apart by a black hole 6 million times heavier. The flare brightened across ultraviolet and X-ray wavelengths for months as the stripped gas heated to hundreds of thousands of degrees. That was not a simulation. It was an observation, repeated now in dozens of confirmed TDEs across the sky. The violence scales with proximity and mass. Neither outcome, fast or slow, leaves anything recognizable. Number 8. Invisible. They emit no light of their own. Not a photon. And yet we map them across the observable universe by cataloging the wreckage they leave behind. Hot gas spiraling inward forms an accretion disk that heats through friction until it glows, first in infrared, then visible light, then X-rays. The Chandra X-ray Observatory has cataloged hundreds of these bright signatures. Powerful jets of collimated plasma launched from the poles at nearly the speed of light shine across entire galaxy clusters like searchlights. When a star drifts too close and is shredded, the debris flares for weeks or months. Background starlight passing near a massive unseen object bends into arcs and rings through gravitational lensing, and those distorted images let astronomers weigh what they cannot see. Then there is the most direct evidence we have. In April 2019, the Event Horizon Telescope, a network of radio dishes spanning the globe functioning as a single Earth-sized aperture, released the first resolved image of the shadow cast by the supermassive object in M87. 2 years later, they did the same for Sagittarius A star, the 4 million solar mass object at the center of our own galaxy. Neither image shows the interior. Both show the unmistakable signature of light bent, trapped, and released at the last possible moment before capture. Add gravitational wave detections from LIGO and Virgo, dozens of confirmed binary mergers heard as chirps in space-time, and the case becomes overwhelming. Multiple independent instruments across every band of the electromagnetic spectrum and now through gravity itself all converge on the same conclusion. These objects are real, and they are everywhere. Number 7. Rogue black holes. Some do not sit still. They wander. When a massive star dies in a lopsided supernova, the explosion can kick the newborn remnant like a billiard ball, sending it hurtling through the galaxy at tens of kilometers per second with no orbit to anchor it and no companion to betray its position. Models based on stellar evolution and supernova rates suggest the Milky Way harbors somewhere between 10 million and 100 million of these drifters. They carry no accretion disk. They radiate nothing. They announce themselves only if they happen to pass between us and a more distant star, bending that light in a brief microlensing event that lasts weeks or months before going dark again. In 2022, a team using 6 years of Hubble Space Telescope astrometry reported the first strong isolated candidate. An object roughly 7 solar masses cruising through the galactic disk at about 45 kilometers per second. Alone, invisible, confirmed only because the light of a background star wobbled by just the right amount. For everyone caught through that alignment, millions will never line up. They cross the voids between stars in silence. No glow, no jet, no advance warning. If one drifted within a light year of our solar system, it would not collide with anything. It would tug. Planetary orbits would shift. The delicate balance that keeps Earth in its habitable lane would degrade over centuries. Comets from the Oort cloud would be flung inward on new trajectories. The probability across any human lifetime is vanishingly small. The galaxy is enormous and the gaps between stars span light years, but the population is confirmed. The wandering is observed and our ability to detect them before they arrive remains close to zero. Number 6. Photon sphere. There is a shell of space around every black hole where light itself is trapped in orbit, not falling in, not escaping, circling on a razor edge. For a non-spinning black hole, described by Carl Schwarzschild in his solution from 1916, this sphere sits at exactly 1.5 times the Schwarzschild radius. At that precise distance, the curvature of spacetime forces a photon traveling tangentially into a perfect circular loop. If you could somehow hover at the photon sphere and look straight ahead, light reflecting off the back of your body would travel away from you, wrap entirely around the black hole, and return to your eyes from the front. You would see the back of your own head. The black hole becomes a lens that folds the universe around you in every direction. The orbit is violently unstable. Nudge a photon a fraction inward and it spirals past the event horizon, gone. Nudge it outward and it escapes into open space. Nothing stays on that edge for more than an instant, and that instability is exactly what produces the glowing ring in the famous photographs. Photons that graze the sphere and scatter outward reach our telescopes. Photons that dip a hair too close vanish forever. The bright ring we see in the EHT images is the knife edge between capture and escape, and it is breathtakingly thin. For a human, the photon sphere is not a destination. Tidal forces would destroy your body long before you reached it, but the physics is confirmed. Zakin, the measured size and brightness of the ring around M87 star match the predicted photon sphere radius to within a few percent, exactly where Schwarzschild placed it over a century ago. Light, the fastest thing in the universe, caught in a closed loop by geometry alone. Number 5. Mass and density extremes. Some black holes weigh 5 times the Sun and fit inside a sphere roughly 30 kilometers across. Others, like TON 618, weigh 66 billion solar masses and have an event horizon that would engulf our entire solar system several times over. But the real surprise is what happens to density as you scale up. A stellar mass remnant packs 3 to 5 suns into a volume smaller than a city. The density is on the order of 10 to the 17th power kilograms per cubic meter, roughly 100 trillion times denser than steel. Add more mass and something counterintuitive happens. The Schwarzschild radius grows linearly with mass while volume grows with the cube, so average density drops. Sagittarius. A star, the 4 million solar mass object at the center of our galaxy, confirmed through decades of orbital tracking by Andrea Ghez and Reinhard Genzel, work that earned them the 2020 Nobel Prize, has an average density lower than water. 66 billion solar masses like TON 618 would have an average density lower than the air in the room you are sitting in right now. Heavier than a galaxy. Less dense than a breath. They grow by 2 routes. Gas and dust spiral inward through a superheated accretion disk, and friction quietly converts orbital energy into mass. Or 2 black holes collide and merge, a process LIGO has now detected dozens of times. Growth sounds limitless, but the universe resists. When a black hole feeds aggressively, it becomes a quasar, and the resulting radiation pressure and powerful winds blast away the surrounding gas, choking the fuel supply. Observations suggest a practical ceiling somewhere near 10 billion solar masses, though the early universe shows quasars that reached enormous sizes within a few 100 million years of the Big Bang, proving fast growth is possible when fuel and mergers align. At the core, general relativity predicts a singularity where density becomes infinite and volume collapses to zero. Most physicists, including Penrose, who proved singularities are unavoidable in his 1965 theorem, so believe that infinity is a signal that the theory has reached its boundary. Quantum gravity, whatever form it eventually takes, is expected to replace the infinity with something finite, but beyond our current ability to describe. We cannot probe the interior directly. What we have are gravitational waves, X-ray spectra, shadow images, and a density paradox that defies intuition. An object less dense than air on average, yet hiding a point where all known physics ends. Number 4. Baby universes. In 1992, the physicist Lee Smolin published a proposal that still makes cosmologists uneasy. He suggested that every time matter collapses past the event horizon and approaches the singularity, the crushing core does not simply terminate, it bounces. And on the other side of that bounce, a new region of spacetime begins to expand, it carrying its own physical constants, its own arrow of time, and its own causal horizon. A baby universe, disconnected from ours, growing in a direction we cannot point to. The math draws from attempts to merge general relativity with quantum mechanics, particularly from loop quantum gravity, where space-time itself has a discrete granular structure at the Planck scale. In those models, the singularity is replaced by a quantum bounce, a bridge between our collapsing geometry and a fresh expanding one. Other approaches rooted in string theory suggest topology changes that allow space-time to branch. Mainstream physics treats these as speculative possibilities rather than established fact. There is no observational test, and no signal can cross back from a child universe to confirm it exists. So critics point to the absence of testable predictions. Supporters counter that the framework is mathematically consistent and that it offers an elegant explanation for why our own universe began with such finely tuned initial conditions. Perhaps it inherited them from apparent collapse. If the idea holds, then black holes are not just endpoints. They are reproductive engines in a cosmic family tree, each collapse seeding an offspring we will never observe. Our own universe, everything we see, every galaxy and void and filament may itself be the interior of a black hole in some larger, older cosmos. We have no way to check. The boundary is sealed in both directions. Number 3. Hidden population. Our galaxy likely harbors between 10 million and 1 billion stellar mass black holes drifting through the disk and halo. Most have never interacted with anything bright enough to reveal their presence. How do we arrive at a number that large when most of them are invisible? The census relies on 4 independent methods, each filling a different part of the picture. First, X-ray binaries. When a black hole has a companion star close enough to siphon gas, friction heats the infouling material to millions of degrees, and it glows in X-rays. Instruments like Chandra and XMM Newton have cataloged dozens of these systems. Second, dynamical measurements. Astronomers track the motion of visible stars, and when those orbits imply a massive dark companion, they infer a black hole. Third, microlensing. A compact mass drifting between us and a background star will briefly brighten and distort the distant light. Surveys like OGLE and MOA have recorded thousands of microlensing events, and a small fraction of those are consistent with stellar mass black holes. Fourth, gravitational waves. Since 2015, LIGO and Virgo have detected dozens of binary black hole mergers, each one revealing a pair that was previously invisible. Every detection adds to the statistical population model. Combine those 4 lines of evidence and the models converge on a range that is difficult to absorb. Tens of millions at minimum, possibly a billion. The nearest confirmed quiet candidate, identified through astrometric wobble by the Gaia spacecraft, sits roughly 1,560 light-years away, far enough that Earth faces no gravitational threat. But step back and consider the ratio. For everyone we have found, there are millions we have not. The galaxy is a graveyard, threaded with invisible remnants of dead stars, each one carrying enough mass to crush anything that wanders too close, each one drifting in silence. Number 2. Hawking radiation. In 1974, Stephen Hawking published a calculation that shocked the physics community. He showed that the space near a black hole event horizon is not truly empty. At the quantum level, pairs of virtual particles flicker into existence constantly. Usually they annihilate each other and vanish, but at the boundary, the curvature of space-time can separate a pair before annihilation. One particle falls inward, the other escapes. To a distant observer, that escaping particle looks like faint thermal radiation being emitted by the black hole itself. So, over time, that radiation carries away energy, and because mass and energy are equivalent, the black hole slowly loses mass. The rate depends on size. A stellar mass black hole, say 10 solar masses, radiates at a temperature of roughly 6 billionths of a Kelvin, so faint it is unmeasurable against the cosmic microwave background. Its lifetime would be on the order of 10 to the 67th power years, a number that dwarfs the current age of the universe by a factor that has no practical analogy. Supermassive black holes are even more patient. 100 billion solar mass object would take on the order of 10 to the 100th power years to evaporate. By comparison, the last stars in the universe will burn out in roughly 10 to the 14th power years. These objects will outlast everything. But here is where Hawking's calculation becomes genuinely disturbing. As a black hole loses mass, it gets smaller. As it gets smaller, it gets hotter. As it gets hotter, it radiates faster. The process accelerates. In the final moments, a black hole the mass of a small asteroid would reach temperatures exceeding 1 trillion degrees and explode in a burst of gamma rays and high-energy particles. No confirmed evaporation flash has ever been observed. Telescopes and particle detectors have searched for the signature of primordial micro-black holes popping at the end of their lifespan, and so far nothing convincing has appeared. That absence constrains how many such objects could exist. The deeper problem is conceptual, and it remains open. If everything that ever fell into a black hole eventually escapes, encoded in that final burst of radiation, then information is preserved, and quantum mechanics survives intact. If not, then one of the most fundamental principles in physics, unitarity, is broken. Hawking himself changed his position on this twice before his death in 2018. The question is still unresolved. Number 1. Warp space and time. Get close to a black hole, and your clock disagrees with every other clock in the universe. A timepiece hovering just outside the event horizon of Sagittarius. A star would tick measurably slower than one on Earth. Not metaphorically, measurably. General relativity predicts it. GPS satellites already correct for a weaker version of the same effect every day. And observations of stars orbiting our galactic center confirm it at the extreme end. From far away you would watch a falling astronaut slow down, redden, and freeze on the boundary, their image dimming over months and years until it fades below detection. From the astronaut's own frame, the fall feels ordinary, even uneventful. The disconnect between those two experiences is not an illusion. Both are correct in their own reference frames. Time itself runs at different rates depending on where you stand in a gravitational field. Space does more than bend. Around a spinning black hole, and most of them spin, space-time is dragged in the direction of rotation. Roy Kerr solved the equations for this in 1963, and the result is a geometry where nothing near the hole can remain stationary. Matter, light. Even empty space is forced to rotate with it, swept along like debris in a whirlpool. The region where this dragging becomes inescapable is called the ergosphere, and it sits outside the event horizon. Roger Penrose showed in 1969 that energy can actually be extracted from this region through what is now called the Penrose process. A spinning black hole is not just a sink, it is a reservoir. Light grazing the photon sphere bends into arcs. Background galaxies smear into Einstein rings. The shadow we photographed in 2019 is larger than the event horizon itself because gravity bends light paths around the hole, inflating the apparent size of the dark region. We see these effects in the orbits of stars near Sagittarius A star. In the redshift of X-ray emission lines from gas whipping around at 1/3 the speed of light, and in the precession of orbital paths that exactly matches Kerr predictions. Events ordered one way in your frame can look reordered to someone standing a fractional light second away. Cause and effect become local observations, not universal truths. If time and causal sequence are not absolute near these objects, then the framework we use to construct reality, the assumption that events happen in a fixed order and that clocks agree, does not hold everywhere. It holds here, in our gentle gravitational well. Step closer to the edge and it dissolves.